Physics does not respect lazy design. A tragic 1989 industrial explosion serves as a stark reminder. When a local hotspot exceeds the strength of the reactor material, the results are catastrophic. Ideal math assumes uniformity, but the reality is that thermal spikes can turn steel structures into failures in an instant. Managing 10,000 tubes in an ethylene oxide reactor is a complex challenge. While ideal models assume perfect heat transfer, in reality, catalyst dust and stagnant layers create dangerous hotspots. AI integration allows us to map thermal profiles across these thousands of tubes in real time, identifying those nearing safety limits. Think of a catalyst pour as a toll booth. If cars arrive faster than they can clear, a traffic jam occurs. In a reactor, that translates to thermal stress. By calculating the Thiele modulus, we understand the balance between reaction and diffusion, allowing AI to dynamically adjust inlet temperatures to prevent hazardous dead zones. Industrial evolution has shifted from simple batch pots to plug flow reactors. We've traded volume for velocity, but this introduces new complexities. Large diameter reactors struggle with flow maldistribution and temperature gradients, proving that simple geometric scaling from lab to plant rarely captures the messy reality of industrial physics. Two-dimensional logic helps us size the reactor, but it cannot manage the dynamics of heat generation and removal. We must move beyond static parameters. Modern AI integration helps by scanning control diagrams to identify missing safety systems before any steel is ever cut. Inside the reactor, we face a microscopic fluid maze. While we might assume perfect packing, the reality is uneven voids and rat-holing, which significantly alter pressure drops. By using computer vision AI on X-ray scans, we can map these 3D imperfections and feed them back into our models for more accurate performance predictions. Physics laws often assume perfect conditions, but the real world is far less forgiving. When coolant reaches the point of film boiling, heat transfer efficiency can crash by up to 90%. This creates a point of no return, where linear assumptions become a fatal error. We can bridge the gap between complex math and reality using real-time AI physics. Physics-informed neural networks, or PINs, allow us to resolve boundary layers for thousands of tubes in milliseconds. This process overcomes the limitations of traditional computational fluid dynamics that assume perfectly smooth surfaces. We are scaling human capability by essentially giving our equipment a nervous system. A digital twin architecture samples physical sensor data at high frequencies using Kalman filters to merge it with models. If a sensor drifts, the system identifies and quarantines it, ensuring the integrity of the data stream. Traditional control systems are reactive, often waiting for a temperature spike before taking action. Reinforcement learning changes this by anticipating thermal waves and adjusting actuators proactively. By learning to compensate for mechanical lag and valve stiction, we can maintain steady operations where traditional systems would struggle. In the field, we face the reality of the wrench and the weld. Uneven catalyst loading can lead to channeling, where fluid takes the path of least resistance. Acoustic AI now helps us listen to the signature of pellets during loading, verifying packing density to prevent dangerous pressure imbalances. Fouling is a silent killer of efficiency. Rather than assuming uniform degradation, we use LSTM neural networks to track heat transfer decay over time. This enables us to forecast exactly when a safety trip will be triggered, allowing for maintenance to be performed before physical damage occurs. We are no longer just designing, we are evolving through generative lattice structures. These complex shapes disrupt the thermal boundary layer, boosting heat transfer significantly. By incorporating manufacturing constraints into the AI's loss function, we ensure these designs are physically viable and not just mathematically elegant. Ultimately, we are building the metabolic systems of our civilization. A plug flow reactor functions as a localized entropy reversal engine, transforming low-value molecules into high-value structures. Despite the challenges of material scarcity and chaos, This approach represents a new standard in industrial orchestration. Physics is unforgiving, but mastery prints money. By replacing lazy tolerances with obsessive, AI-supercharged first principles, we can achieve substantial gains in yield and efficiency. We cannot defeat entropy, but with the right tools, we can manage it. Now, let's get back to the shop floor and build it right.